Hello, AP Physics students of the future. I am Noah Benjamin,
And I'm Luis Quinones.
and we're talking buoyancy. True. Okay, if we look here at the physical example of a cork in a water vessel, what we can observe is that there has to be an upward force in this situation because there's definitely a downward force from gravity and the cork's not moving. Go.
So, like Noah said, there's going to be an upward force on the cork. So if we can draw a free body diagram, here we have the cork. So we know that because the cork is on Earth, there's going to be a downward force due to gravity. That's going to be the force of gravity. And just like we established, because the cork is floating, there's going to be an upward force. That upward force is going to be the buoyant force. So if we look at our equation for force, force equals mass times acceleration. But because the object is not accelerating, it's going to have a net force of 0. So what this means is that the buoyant force is going to be equal to the force of gravity on this object.
So one important thing to understand is that there's buoyant force applied whenever there's an object in a fluid. So not only if it's floating, and that actually means that there is an upward force right now on me from the air, and that's a buoyant force. So it just depends on a fluid being in the same system as an object, and not whether the object is floating. And the actual rules of floating will be talked about by Luis.
Alright, so for an object to be able to float, it has to follow certain rules with density. So for an object to float, it has to have a lower density than the object is floating in. So for the situation with the cork and the water has a higher density than the cork, allowing the cork to float.
Put you on the. Okay, so now let's look at the actual physics and math behind this. So our equation for the buoyant force is going to be this symbol is rho. It just means density. So it's the density of the fluid that you're talking about times the acceleration due to gravity on Earth, 9.8 meters per second squared, times the volume of displaced fluid. So that's our equation, and it's a bit counterintuitive at first, but there's a few ways to understand it that I think are useful. So remember that the buoyant force is the force applied by a fluid. So if we look at here, we have like a column of fluid, a hypothetical fluid, and I put little blue dots to indicate where the water molecules are. So you have a higher concentration down here, higher density, or higher pressure. You have P2, then P1 up here, and that's just due to the force of gravity on this column of liquid. So you have two forces here, right? Because pressure equals force over area. These areas are the same. So F2 is going to be greater than F1 because you have a higher pressure here. And so if we're looking at the force that this column of fluid applies, it's going to be the second force minus the first force, and it's going to be in the upward direction. So that's our buoyant force. So if we look here, we have the buoyant force equals F2 minus F1. Just substitute in with our formula relating pressure, force, and area, and we get this. You can bring out the subtractions of pressure, and you have the change in pressure times the area And so the change in pressure, there'll be later videos on this, but it's calculated by this little multiplication here of the density of the fluid times gravity times how deep in the fluid you are, the height, and then you have height times area, so you get all the way back to rho of the fluid, density, gravity, and volume. Yeah.
All right, so after doing all of this, we get back to our equation of rho, density of the fluid, times gravity, times the volume. And from previous equations, we know that rho times v is just going to equal the mass of the fluid times gravity. That will all equal the weight of the fluid. And so this way is a little complicated. It involves pressure and area and different ideas. So a more simpler way to do this would just be look at our equation of F equals ma. And since we're working with a liquid, mass is going to be V times rho. So it's going to be force is going to equal the density of the liquid times the acceleration, and that's going to be the acceleration due to gravity times the volume of the displaced liquid.
Right on.
So let's look at buoyancy in some more conceptually. So if we have this free body diagram of this block of wood, let's just say in a liquid. So there's going to be some percentage of this block in the liquid, and it's just going to be that right there. That volume right there is going to be how much is displaced by the fluid. So if we look at our equation previously, that Fg equals the buoyant force, then if we expand that out, we get mg equals rho gv. So then we have g on both sides, so we can just cancel those out. And so now we're going to be solving for volume, so we're going to have m over rho equals v. So this mass right here is going to be the mass of the block, and the rho is going to be the density of the fluid. So it's a very cool way to see that the volume that's going to be displaced by the fluid is equal to the mass of the block divided by the density of the liquid. Alright, so let's look at some more conceptual situations involving a block of wood suspended in a liquid with a string attached to it. So this object here would float without the tension due to this massless string, just to say. So if we draw a free body diagram of what's going on here, so we have the object here, there's going to be the force of gravity on the object, and then the tension in the string is also going to be pulling down. So then the force upward is going to be the force, the buoyant force. And so with this equation, we have that Fg plus T equals the buoyant force. And so if we expand this out more, we can get it to solve for tension. It will be that tension equals the buoyant force minus the force of gravity. And we can expand that out a little bit to the point where it's rho gv minus mg. So that's just to solve for the tension in this situation. In this situation, the buoyant force is going to be greater than that it would be if the object did not have the string, just because that there's be more volume displaced. And if we look at this situation here as well with an object that would not float but being suspended by a string, we can draw another free body diagram here, being here's the object. This would be the force of gravity down, the buoyant force up, and then also the tension is also going to be holding it up. So in this situation, we have F of g equals the buoyant force plus tension. Again, we're solving for tension, so we just have to move the buoyant force over. Tension equals F of G, subtract the buoyant force. So in these two situations, the equations just flip. We can expand them out again if you want to. Equals. And so there we have the equations for the tension of the string in these two different situations where an object that would float is being pulled all the way under the water, an object that would not float being suspended in the liquid.
Right on.
So that was an overview of the buoyancy equation and some concepts involving buoyant force.
Signing out.